So very easily, see if you observe, I'm not using any quantum calculations here. The force of attraction between the body and the earth. Now the satellite is orbiting in a circular orbit. The expression for escape velocity, this has to be in seconds. Time has to be in seconds. Hello students, this is SD sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. In my yesterday's session, we have solved problems which have appeared in the earlier annual examination from the chapter Gravitation, where you have seen if we have the sample space of the concept, solving any numerical becomes very, very easy. Again today, I will be working out few more problems. Let us solve further problems from the chapter. Now, the next question says, calculate the orbital velocity. We are asked to calculate the orbital velocity and period of revolution of an artificial satellite. Artificial satellite at an altitude of 200 kilometers. Radius of the earth is given. Mass of the earth is 6 into 10 power 24 kg. Gravitational constant. So with this data provided, I will have to calculate the orbital velocity of the artificial satellite. So, as we did in the previous class, first we will note down the data. So, what is the first data? Altitude. Height is given. So, height is 200 kilometer. So, 200 into 10 power 3 meter kilo, which I also write as 2 into 10 power 5 meters. Again, radius of the earth is given 64 into 10 power 5 meter, 6,400 kilometer. Mass of the earth is given 6 into 10 power 24 kg. So with this data available, I will have to calculate the orbital velocity and period of revolution. So first, I will calculate the orbital velocity of the satellite. So V0, which is root GM divided by R plus H. So if you remember, this is the expression for orbital velocity, root gm divided by R plus H. So this is G, gravitational constant, 6.67 into 10 power minus 11. Mass of the earth is given 6 into 10 power 24 divided by R plus H. R was 6,400 plus 200 into 10 power 3. Simplifying this, first we will simplify the numerator. 6.67 into 6. 6.67 into 6 is, so this is root of 40 into 10 power 24 minus 11 is 13 into 10 power minus 3 divided by 6,600. So this is 40 divided by 6,600. So this is root 0.006 into 10 power minus 3. When we simplify this, orbital velocity turns out to be nearly 7.7 kilometer per second. So, simple simplification, 7.7 kilometer per second. B, time period of revolution of the satellite. Generally, how do we describe time? Distance by speed. Distance divided by speed is time. Now, the satellite is orbiting in a circular orbit, circumference. So, 2 pi r, but here it is r plus h. Speed is nothing but orbital velocity. On simplification, it turns out to be 5,400 seconds. So students, please do substitute, then verify the answer. Don't directly take down the answer. The next question. We are asked to calculate the mass of the sun given the radius of the earth is 1.5 into 10 power 8 kilometer and gravitational constant is so much. Now, I will first collect the data. Radius of the earth in this case is 1.5 into 10 power 8 kilometers. 1.5 into 10 power 8, which on simplification is 10 power 11 meters. Again, I told you, kilo. So many kilometers. So 10 power 11 meter. Gravitational constant 6.67 into 10 power minus 11 Newton meter square kg minus 2. This is an established constant. You should have it at the tip of your tongue. Now, before we proceed, I'll consider the time period to be 1 year. And as I told, this has to be in seconds. Time has to be in seconds. The reason is it is SI unit. So, 365 days. Each day is 24 hours. Each hour is 60 minutes. Each minute is 60 seconds. So when I simplify this, 365 into 24 into 60 into 60. And to avoid complication in terms of powers of 10, always use powers of 10 to avoid the complication. So this is 3153 into 10 power 3 seconds. So much will be the time. Now, the mass is calculated, mass of the sun is calculated using the formula 4 pi square r cube gt square. Always know this. This is the direct formula used to calculate the mass of the sun. So this is 4 into 3.14 whole square into 1.5 into 10 power 11 whole cube, 6.67 into 10 power minus 11 into the value of t, 31536. 31536 into 10 power 3 whole square. So when I simplify this, this is 4 into 6.28, 1.5 3 times whole cube. So 1.5 into 1.5 into 1.5, 3.37 into 10 power 33 divided by 6.67 into 10 power minus 11 into, when we simplify this, I keep it as it is. Use your calculators to simplify this. This turns out to be a huge number. So from this, the mass of the sun is approximately 2 into 10 power 20 kg. So the simplification turns out to be 2 into 10 power 20 kg. The next one. Calculate the escape velocity of a body. Escape velocity of a body. If the mass of the earth is 6 into 24 kg and radius is 6,000 kilometer. So he says, again radius is 6,400 into 10 power 3 meters. Mass is 6 into 24 kg. We are asked to calculate the escape velocity. So let us recall the expression for escape velocity in terms of mass and radius, students. So escape velocity is root of 2gm by r. If you have recalled, the expression for escape velocity is root 2gm by r, or this is 6.67 into 10 power minus 11, 6 into 10 power 24 divided by 6,400 into 10 power 3. So when we simplify, again we will simplify the numerator first. So it is 2 into 6.67 into 6, which gives me 80 into 24 minus 11, 10 power 13 divided by 64 into 10 power 5 root. I've just made this in powers of 10. 80 divided by 64. So this is root 1.25 into, this becomes minus 5. 13 minus 5 is 8. Or when you simplify, this turns out to be 1.11 into 10 power 4, or which is approximately 11 kilometer per second. So very easily, see, if you observe, I am not using any quantum calculations here. Only the expression, suitable simplifications, I am arriving at the answer. Again, to calculate the escape velocity, I am giving this as an assignment. Take out your calculators, papers, pen, and work this out. This is an interesting problem now. The problem says a body has a weight of 81 Newton on the surface of the earth. So this is the earth. I assume this to be the earth, center of the earth, radius is r. When the body is on the surface of the earth, it has a weight 81 Newton. So I know F1, the force of attraction between the body and the earth, is G m small m by r square. So how much is F1? It is already given. 81 equals G m small m by r square. I call this equation 1. What will be its weight when taken to a height equal to half the radius of the earth, I will have to calculate the weight when the body is taken to a height. It is taken to a height above the surface of the earth, which is half the radius of the earth. So in this case, now again, this is the earth. The radius was r. Now the body is taken to a height which is half the radius. So in this case, what will be the weight has to be calculated. So again, F2 is G M by, now this is R plus R by 2 whole square. This R plus R by 2, height half the radius of the earth, or F2 equals GMM divided by 3R by 2 whole square, or F2 equals 4 GMM by 9, equation 2. So if I divide F2 by F1, so if we are dividing F2 by F1, so what remains when we divide F2 by F1? Or F2 will be equal to 4 by 9 into 81. This gets cancelled. The same in the previous, 4 by 9 into 81. Or F2 is 36 Newton. So, simple understanding of the problem has yielded the answer. So, you people also pick up numericals from the textbooks. Try to get the relations and solve them. In my next session, I start up with work, power, energy. Thank you.